We'll now analyze the running time of Quicksort. Just like merge sort, Quicksort is a recursive algorithm. And what that means is if we're going to analyze it, we're going to have to use a recurrence relation, just as we did when we analyzed the merge sort algorithm. So for this analysis, we're going to assume that the pivot is randomly selected, and we're also going to assume that there is no cutoff for small arrays. We can modify this, but it would make the analysis more complicated. So this will allow us to give a more simplified analysis for the algorithm. So we'll let t of 0 be t of 1, which is going to be 1. So what we're saying here is if the array has 0 or 1 element in it, then it's just going to be a constant time operation. Now what about in general? Well, the running time of the algorithm is going to be the running time of the two recursive calls, because we're partitioning our array into two different arrays. So it's going to be the running time of those arrays. And then we have the time spent doing the actual partition, which is linear time. So what this means is t of n is actually going to be t of I plus t of n, n minus I minus 1 plus c times n. So how did we get this big formula? Well, I in this case is going to be the number of elements in S1. And then n minus I minus 1 is going to be the number of elements in S2. So what we're just saying here is we're taking the running times of performing quicksort on S1 and S2, and then we need to add in the time it takes to do the partitioning. Now, what we'll do here is we'll look at the worst case, the best case, and the average case for Quicksort. Let's start by taking a look at the worst case scenario. And in this case, it would be that the pivot is the smallest element every single time. That is the absolute worst case scenario. What this means is I is going to be 0. And let's just suppose we ignore the fact that t of 0 equals 1. Our recurrence relation is going to be that t of n equals t of n minus 1 plus c times n, where n is going to be greater than 1. So how do we solve this? Well, we can use the same telescoping approach that we use for the merge sort algorithm. And if we do that, we would find that t of n is equal to t of 1 plus c times the sum of I, where I goes from 2 to n. And though that sum, it turns out that we would get theta of n squared. And this does make sense when you think about what would actually be going on in this case. The size of one partition per iteration is O of n, and we would have O of n iterations. Therefore, it does make sense that this would turn into theta of n squared. We'll now take a look at the best case scenario, and this would be if the pivot is always in the middle of the array, which means every time we make a recursive call, we can assume that the two sub-arrays are going to be exactly half the size of the original array. So every time we partition it, it's always half of each other. So that means the two sets have the same size. This means our recurrence relation would be t of n equals 2 times t of n over 2 plus cn. So if we decide to divide both sides by n, we would have t of n over n equals t of n over 2 divided by n over 2 plus c. So then if we use the telescope approach with this equation, and then we add all the respective terms, what we would get is that t of n would be t of 1 over 1 plus c log n. And if we multiply everything by n, this means that t of n is going to be n times t of 1 plus c times n log n, or in other words, this would turn out to be theta of n log n. And we see that this is the exact same analysis as we did for the merge sort algorithm. Now, what about the average case analysis? Coming up with this case is actually very difficult and very complex. So we're not going to worry about going into the nitty-gritty details of this particular analysis. We could spend an entire week going over this analysis and it would still be very complicated. But we will say a couple things about it. For the average case, we would assume that each of the sizes for S1 is equally likely. So it's equally likely that S1 has 0 elements, 1 element, 2 elements, and all the way up to n over 2. Actually, it goes all the way up to n minus 1 elements. So that means that each size has probability 1 over n. And what we would find is that in the average case, t of n turns out to be O of n log n.